Okay, we're going to talk about acids and bases. We'll start off with acids. Acids are substances that produce hydrogen ions or H3O plus ions when you dissolve them in water. Hydrogen ions are protons. If you remember, a hydrogen atom just has one electron and one proton. Ions lose their electrons or gain. In this case, it loses the electron. All that's left is the one proton. We also have hydronium ions, in which a water molecule has gained an extra hydrogen ion, and so it's H3O plus. So both of these have a positive one charge. So anything that makes hydrogen ions is considered an acid. And here we have a few examples. We have hydrochloric acid, which is found in your stomach. We have acetic acid, which is basically vinegar, found in fruits and vegetables, salad dressing, and then our fruits, citrus fruits, citric acid. Note that in all three cases, we can tell that it's an acid because the very first element in the compound is H, for hydrogen. So that's one way to recognize acids, is they start with H. Furthermore, the number of hydrogens in the compound will match the charge of the negative ion that would form once they split apart. We call that dissociate when they're dissolved in water. So hydrochloric acid, HCl, splits apart into H plus and Cl minus ions, so one hydrogen in that case. Same thing for acetic acid. We have the acetate ion, C2H3O2, negative one charge, so only one hydrogen ion. But notice that the citric acid has 3 hydrogens to match the negative 3 charge of the acetate, or excuse me, the citrate ion. So these are some examples of acids. Anything that produces hydrogen ions. Go over some properties of acids. First off, the word acid comes from the Latin word acidus, which means sour, and acids have a sour taste. Think of lemons and limes, for example. Acids break apart into ions, and so they conduct electricity. Acids corrode metals. They eat metal. There was a movie a few years back called Dante's Peak, in which the boat's bottom, which was metal, actually gets eaten away by the acid that had formed in the lake. So they corrode metals and produce hydrogen gas, H2 gas. They also corrode carbonates, limestone, marble, concrete, and produce CO2. Just last week, we poured acid on the concrete discus ring out at the track because it had gotten too smooth. So putting a little acid on it ate away some of the concrete. That's kind of what the corroding does, eats it away and makes it a little bit rougher so it's not so slippery. Acids, of course, neutralize bases. So sort of counteracts the properties of a base. and acids change blue litmus paper to red. Bases. With acids, we had one definition, anything that produces hydrogen ions. With bases, we really have two definitions. The first one, they produce hydroxide ions, OH minus ions, when dissolved in water. This is the Arrhenius definition. This was the original definition, if you will, for bases. Kind of the opposite of the acids. Acids produce hydrogen, these produce hydroxide. However, it was found later on that there were substances that acted as bases that didn't have OH ions in them. They were not also containing OH, and so they had to broaden the definition. And so they decided, and this was Bronsted-Lowry definition, that anything that accepts a hydrogen ion would also be called a base. So we have some examples here. Notice that the first three all end in OH. This is an easy way to tell a base. If it ends in an OH, then it's a base. And then we have a couple of bases that don't have hydroxide ions in them. Baking soda, NaHCO3, and ammonia, NH3. Now, one of the things you'll have to do later on is there'll be a question or two in which it would be something like, well, which one of these is not an acid, or which one of these is a base? You'll have to be able to answer that question. In other words, be able to always recognize acids or bases just based on their formula. Just as with the acids, notice that the number of hydroxide ions I have matches the charge of the other ion. In other words, just like acids split apart, bases split apart into two ions, a positive and negative ion. The OH is a negative ion. Sodium, for the first case, sodium hydroxide, a positive ion. Well, there's one sodium, it has a +1 charge, so we have only one hydroxide ion. But with magnesium and calcium, since they actually have +2 charges when they become ions, notice that we form two hydroxide ions in those cases. So twice as many with the +2 ions. And if we had a +3 ion, then we'd have 3 hydroxide ions in there. So just as the acids have the number of hydrogen ions that matches the negative charge, these negative hydroxide ions have as many as will match the positive metal, usually metal charge. Sodium hydroxide, many bases are part of cleaning product soaps. Antacids, magnesium hydroxide, think Pepto-Bismol. And then lime, whitewash, plaster, that kind of slick white stuff that you sometimes see in construction, calcium hydroxide. Properties of a base. Bases, also called alkaline, which comes from the Arabic word for ashes, alkali. If you might remember, we've had the word alkaline before. We call them too the alkaline earth metals. And in fact, many of those metals will form bases when connected to hydroxide ions. And they're called alkaline earth specifically because they were thought to be part of the earth. You have a fire, the bones were still left behind, calcium in the bones, etc. Acids have a sour taste, bases have a bitter taste. Chocolate is very, very bitter. If they did not add all that sugar to it, it would be extremely hard to eat. Bases feel slippery. Remember that they're often found or made into soaps. They corrode fats and oils and waxes. Again, they're used as soaps and cleaners. So think the kinds of things that you might see advertised for cleaning up in the kitchen after cooking, and you want to get the oils or fats off of dishes or pans that you've cooked with. Just like acids, these will conduct electricity because when dissolved in water, they will dissociate, break apart into ions. Acids neutralize bases, bases neutralize acids. And bases change red litmus paper to blue. So they're kind of opposites, but they also kind of complement each other. One neutralizes the other. One kind of cancels out the other. Okay, as I said, they kind of go together, and you're generally going to find them, if you look at a chemical reaction, you're going to find them in pairs, okay? Because again, one way of looking at them is they're related by the loss or gain of that one hydrogen ion. Something has to lose the hydrogen ion, something else has to gain it. And so, as in our example here, HNO3, nitric acid, you mix that in water, it dissolves, and it forms hydronium, H3O plus ions, and nitrate ions, NO3 minus. Now, basically, the HNO3, the acid, lost its hydrogen, donated its hydrogen. The water picked it up. So the acid is considered, or the HNO3 is considered the acid, donating the hydrogen. The H2O is considered the base because it accepted the hydrogen to form the hydronium ion, the H3O plus. But they work in pairs too. In other words, if I think about going in the opposite direction, and very often this will happen as well, the NO3 minus, the nitrate ion, in the opposite direction will receive the hydrogen ion to reform HNO3, so it is considered the conjugate base, because in the other direction it would receive the hydrogen ion, where the H3O plus is considered the conjugate acid, because in a reverse direction it would lose that extra hydrogen to reform water. And so we have our acid and base on the one side, but we have what are called the conjugate acid and base on the other. If we were thinking in terms of a reverse reaction, in other words, the two ions coming back together to reform the nitric acid and water that they originally were. So they always act in these pairs. Now, anytime we mix acids and bases together, we're going to make salts. A salt is any ionic compound. Remember, ionic compounds are metals and nonmetals joined together due to their electrostatic attraction. Positive and negative ions, opposites attract. Anytime these are formed from the reaction between an acid and a base. And here are some examples. Hydrochloric acid and sodium hydroxide. Notice again the hydrogen at the beginning of the acid, the OH hydroxide ion at the end of the base. Well, when they react together, they form sodium chloride, table salt, and water. Hydrochloric acid and KOH, potassium hydroxide, form potassium chloride, KCl, sometimes considered a salt substitute for people who have to restrict how much sodium is in their diet. And then the last example, we have phosphoric acid, H3PO4, and calcium hydroxide. They combine to make calcium phosphate and water. Notice that in all three cases, we are making water. So we make a salt and water. Okay, pH scale. How we measure basically how strong or weak acids or bases are. This is a logarithmic scale. Goes from 0 to 14, but basically the 0 to 14 correspond to the exponent of the concentration of hydrogen ions in the solution. So note on the screen there that we have a pH of 7. Well, that would be with a 10 to the negative 7 capital M for molarity, moles per liter. And so the pH scale, instead of actually looking at the concentrations, because they're very, very small, ranging basically from 10 to the 0, which would be 1, to 10 to the negative 14, which would be 0.000, 13 of them, and then a 1. So very, very tiny concentrations for the very weakest type things, acid-wise. They are used to measure the strength of these things. We basically break them up into 3 groups, if you will. 7, that's neutral. Okay? A lot of things depend on it being very close to neutral. Anything that's less than 7, or its pH value, is considered an acid. Anything that's more than 7 is considered a base. And then we have some examples, and we have done some subdividing here. So we have our strong acids. Basically, they have pH values of 0 to 3. Our weak acids, 4 to 6. Our weak bases, 8 to 11. And our strong bases, 11 to 14. Now, they do not have to have whole numbers. We're just simplifying things here by talking about the whole numbers. So, for example, if the pH of something was 6.6, that would still be a weak acid. It's a little bit less than 7, so it's on the acid side of things, and it's in that weak range. To be a strong acid, it would need to be 3 or less. Same thing as if we had something with a pH of, say, 7.2. It's a little past neutral. That would be a weak base. And then you have some examples here. Concentrated lemon juice would be a strong acid. There are peppers that you may eat as part of a meal that can burn you. Those are very strong acids. Weaker acids that you can eat, milk, soda, vinegar. And then, as I said, many cleaning type products end up on the base side. Milk and magnesia for upset stomachs, counteracting the acids in your stomach. Yes. It's possible, but this is the majority of everything. Ammonia, bleach, those are in the strong type base categories. Also notice that I have a little bit of color coding going on here. We will have a lab next week in which we'll have to actually match a color with a broad range, 0 to 3, 4 to 6, so we can identify weak acids, strong acids, and so forth. It's kind of right in the middle. So, you know, strong or weak, it's in the middle of the bases. Okay, here's the last slide for today. Neutralization. We already talked about adding an acid to a base to make salt and water. That's called neutralization. Now, if they happen to be exactly equal in strength on opposite sides of neutral, then we would actually just get salt and water. However, if we're adding a strong acid to a weak base, they'll only be partially neutralized. It would turn into a weak acid more than likely. So we can, you know, go along the continuum, but to actually totally neutralize it, you would have to have proportional amounts of the acid and the base to counteract each other. Please note, it makes salt and water, not salt water, not seawater. Those are considered particular kinds of things. The particular kind of salt we make depends on the acid and base involved. And so it's better just to say salt and water, not think seawater, which has all kinds of different salts in it. And then we also have the term buffer. Basically, a buffer is a substance that resists changes to pH. It's made up of an acid and a base. Our bodies have buffers in them. Sometimes medicine has a buffer connected to it, so it won't upset our stomachs. But buffers basically are so we can eat things that are slightly acidic or slightly basic, and it gets counteracted so that it doesn't upset our system. Many things require the pH to stay within a very narrow range to exist or work properly. Buffers serve that purpose.